I have a few of the homeworks that I wanted to talk about, and you might have a few that you want to talk about as well. So let's just take a look at the ones that I've picked, and then I'll open the floor to whatever you've got on your hearts. So this first one, I know you did number 1, but number 1 was in the back of the book, and so number 2 was not in the back of the book. I thought we could use this just to remind you what it means to be an improper integral. If you hopefully watched the videos yesterday and were able to catch up and figure out everything. Anyway, remember improper integrals just mean there's some sort of infinite, something infinite. So we're looking for infinity somewhere. This, not improper, not improper. There is no infinity anywhere. But this one is improper, improper. And the reason why we know this is improper is because if you remember, the tangent of x has asymptotes at all of the right angles. Here's what the graph of tangent of x looks like. And so you have this infinite, this place where the limit as tangent goes towards pi over 2 is either positive or negative infinity, depending on which side of the axis you're on. So similarly, this, well, no, not similarly. This one's different. Let's do C. C is improper. And you might say, well, what's wrong with C? Well, the problem is with, I believe, that one. No, not that one. It's the other one. Sorry. This one. If you plug -1 into this fraction, you get 1 over 0. Is that right? -1 squared, yes. So that you end up with 1 over 0, so you have infinity. So that's improper. And of course, I can't think of anything more improper than having infinity as one of your limits. So each one of those are improper, except for the first one. The first one's not improper. By the way, just before we move on, did anyone have any questions about any of the ones from number 1? Like, why is it improper? Hopefully you checked the back of the book. But anything about that, identifying improper versus proper integrals? Yeah, what do you think, Red?
What about D for the first one?
For the first one, so the cotangent, so here again, they're expecting you to know what the graph of cotangent looks like. You could graph it on your calculator as well, but cotangent has asymptotes at 0, pi, 2 pi, and so forth. And so you have this as the, another way to look at this is that cotangent of x is the cosine over the sine. And so the sine is 0 at x equals 0, so there's a problem there. So yeah, letter D, improper because of the 0, basically. Anything else about this first set? All right, let's move on. I'm going to skip a bunch of them, but we can come back to them if you have issues with them. So let's see. Oh, here's one. I guess I didn't skip all that many. I thought this would, just to remind you how you do these. I know we went over them yesterday, but I don't know if you were watching the videos on 2-speed or what. So here's the way we do this. And I just wanted to run through this one more time, just to make sure that we all get it. And this is a pain. I remember, I was your age once. I didn't want to write all this stuff down, but it's the right way to do an improper integral is to turn it into a proper integral and a limit. So you have the limit as b approaches infinity of this thing, and then you go through the motions of figuring out your antiderivative and then doing the actual limit. So here's the actual limit. And if you don't believe me, you can actually rewrite this as 1 over 5e to the 5b. And as b approaches infinity, this indeed goes to 0. So there's that one. I guess I don't know, why did I do all of these? Maybe because you had to do them. That one was not all that impressive. I guess you had this integration by substitution. We can come back to that one. That's not all that exciting. Here we go. This one was exciting to me because you had to recognize that this is improper because of the bottom limit. So the -2 is makes the denominator 0, so that one is an improper integral. And so, of course, you're going to do this. There, put it there. So that you have a limit as a approaches -2 from the top. And that I know is confusing for some students, so I just want to emphasize that what we care about is we care about what's happening between -2 and 14. That's what the original definite integral is the limits. And so it's the things between those. We don't care about what's happening less than -2, just between -2 and 14. So that's why this plus is here. We don't care what happens when you have a number less than -2, just the number's bigger. And so that's all that means. And then the rest of this is pretty straightforward. And the limit feels very much like a two-sided limit, but it's a one-sided limit. And so I ended up with 32/3 after doing this. And then, let's see, we had a couple more that I wanted to point out. Oh yeah, okay, so here, what could be improper about 1 over x to the 4th? There's no problem at x equals -2, no problem at x equals 3. The problem occurs in the middle, so you have to recognize that there is a 0 is between -2 and 3, and that is a problem. And so that's why I'm going to separate this into two separate integrals. Wow, that's kind of hard to see. But anyway, you can see what we're doing here is we're going to have the limit as b approaches 0 from the top for this interval, and then we go from from the bottom. Sorry, the b approaches 0 from the bottom for the -2 to b, and then from a to 3, you do the integral from the limit as a approaches 0 from the top. So you're kind of coming at 0 from both directions, and those are both pretty easy integrals. The problem happens when you actually try to evaluate those, and you get down here, and you're like, how can I do 0? It doesn't matter which direction you approach 0 from, that's going to be a problem. And so this thing diverges. Both of these are problems. 1 over 0 is diverges. So that's the deal with that one. I guess I was just I pointed at this one just to point out that the problem here is x equals 1. So you would do the same thing, separate this into two integrals where x equals 1 is the separating, the place you separate. And then one more, because I thought maybe some of you wouldn't remember how to do integration by parts, although you're going to have to do it on the test on Friday. And that is this one. So the problem here is 0. The natural log of 0 is undefined. And so we're going to approach 0 from the top because we only care about what's going on between 0 and 1. And then you do your integration by parts. So I've got that over here in green, which I guess you could pause and look at. But the important thing, though, is that I ended up with this thing actually had a limit, and that limit was -1/4. Yeah, by the way, as before, whenever I do integration by parts with a definite integral, I kind of separate off to the side, do the work, and then I say, okay, there. To figure out where I was, that green arrow is not really pointing in the right direction here. I can fix it. There we go. There. So that's where I put my answer for the integration by parts, and then I can do my limits. So I thought those might be the ones you'd have questions on, but I'm happy to hear the other questions you have, if you have any. Wow, so either I figured out which ones you were going to ask about, or maybe you didn't do the homework. Oh, yeah, you didn't know. No, he's saying, yeah, I see you nodding back there. So. Okay, so, all right, well, if you don't have any other questions, I have quizzes for you. So let's take a look, see how you do. And just to remind you, please do upload those homeworks. My understanding is that some of your engineering classes have you upload your homework, maybe? So hopefully you know how to do it. I had someone email me yesterday saying, I'm still not sure how to do this. So if you're still having trouble, I'm holding off putting grades in, but I'm going to have to before I submit my midterm grades next week. So please put something up there. And if you're still not sure, come see me after class. I will help you, and we'll get it done. So here you go. Separated into these. Hopefully there's enough. A couple for you. You'll take the hit. You'll take a 0. got an extra in case. And you guys have enough? Oh, good. Anyone else want one? Perfect. All right, I'll put it up on the screen for those who are watching from home. And then give you a few minutes to work this one out. And I just want to point out, once again, these are quizzes, so they don't matter as much to me. But I do want to get you into the practice of writing down the limit. So this is an improper integral. Write down a limit and, use proper notation. If you're not sure what that notation is, then I guess you'll be learning about it when we go over the quiz. Looks like some people are finishing up. Once you're done, go ahead and turn your paper over, send it towards the middle. I'll come get what you have. If you're still working on this, try to wrap things up in the next minute or so. Shouldn't take you too long. Thanks, Ben. another minute or so, then you can show me what you got. I'll be right back. All right, let's go down. Check up here. I do have them all except for that back row. Excellent. You got a box. I love boxes. Very nice. All right, I think I've got all of the quizzes. Is that right? All right, I don't want to show my answer before. Okay, so here's what I've got. I should say that if you've got a limit, even if you don't know how to do your, well, you should know how to do your antiderivatives by now, but most of the issues that it looked like you were, any problems, it's the antiderivative. So maybe I should point out how to do an antiderivative. But in this case, so here's the issue. So if you've got this written down, you're halfway there. So let me just copy this and paste it over here so you can see how do we do this antiderivative. So just to remind you, the u substitution, I kind of did it in my head, but u is equal to x plus 1, du is dx, and so this thing becomes 1 over u squared, and that's the same as u to the negative 2. And don't forget you're adding 1. So I saw a few people subtracted 1 because you're thinking derivative, but you're adding 1, so this becomes u to the negative 1 over negative 1. So that's why I ended up with this expression over here. Anyway, there's the rest of it. 1 is the answer. Hopefully, if you got 1/3, that was because you subtracted 1 instead of adding when you did your antiderivative. All right, we do need to move on, but if you do have issues, further issues with the homework, please feel free to hit me up later. We're going to move on to arc length. This is, we're back into applications. So I know that you all enjoyed all of our applications, the solids of revolution, the work problems. Do you remember those? And we're doing the same thing with a few other problems that are going to be, we're going to figure them out in a similar fashion. And I just want to point out that the way that these work, the way that you do all of the problems that are the applications that we've been doing, the applications of integration, is you come up with a summation of something, and then you do a limit as the size of your little intervals goes to 0, and that magically, well, not magically, it turns into a definite integral. So that's sort of the program, or the thing that we're going to try to do with each one of these problems. And so arc length is no different. How do we find the length of a curve? Well, that's what we're going to try to do here. As I kind of mentioned or hinted at, the idea that we're going to use is we're going to take this curve and we're going to divide it into smaller chunks and find the length of all the chunks, add them all up, and then get the arc length that way. So we need to make sure that we have a continuous curve, because if it's not continuous with any jump or anything like that, then there's going to be a problem when we set this thing up. Because this is the way we're going to set this up. We're going to have our curve, and we've got those nodes, those values of x. The delta x, by the way, just so that we can see where this is, delta x is the size of the gap between those nodes, and then we're just going to compute the arc length by computing just distance. We all know the distance formula. In fact, let me go ahead and we'll put the distance formula over here. You don't need to draw this picture, but this you probably do want to draw, and that is that if I have 2 points, so let's see, I've got my curve. Let me just pick 2 of the points. Okay, there we go. There's my curve. This is going to be the point x, f of x. And then over here somewhere, I've got another point, x plus delta x, and f of x plus delta x. So now your job is to come up with the distance between those 2 points. Distance. And then I'll pick a few people. Oops, I shouldn't have shown you that. Hello. Yeah, okay, hint. Whoa, no. You're going to have a radical. Oh, come on. Okay, there. Go ahead, jot down distance, share it with a friend, make sure that you have the same distance formula for this. The blue line distance is what I'm interested in. It's probably a little early to be sharing, is that the deal? Okay, well, let's see how you're doing, because you've written down something. Bin P. What do you have? What's the start? You don't have to tell me the whole thing if you don't want to, but you could. What does your distance formula look like?
Subtracting the 1 point, like y.
The y value from one point and the other one. Yeah, very good. Let me get that started. Whoops. Just a minute. Why is this doing this? There we go. Just move this over here so that I can, there. Okay, so Ben is saying we're going to subtract the 2 points. Absolutely. So are we going to do the same with the x values? Sure. We'll do the same with the x values. So here's what it looks like when you subtract the x values. I'll take this one first. So normally when you do distance, you probably think of x2 minus x1, something like that. But I don't have x2 and x1 here. I've got x plus delta x. And then I'm going to subtract off the other x value. Okay, very good. And then you want me to do the same thing with the y values, so I'll do that. And once again, probably with your distance formula, you're used to y2 minus y1, but I'm going to write it the way Ben suggested and do f of x plus delta x minus f of x. So that's the difference of those two y values. Okay, excellent start. Let's find another rando to do this next step. Oh, not here. Ryan, what am I going to do with those differences?
Square them and add them together.
Ooh, good point. Square them and add them together. It kind of is reminiscent of the Pythagorean theorem. Let's do that. Square them and add them together. I like it. One more step that we need to do, and we'll get it from Ben in the back. Ben, what's the last thing that you need to do? The square root, exactly, because when we square those and add them together, what we're going to get is we're going to get the square of that distance because of the Pythagorean theorem. And so, yeah, do the square root. Very nice. Now, at this point, unfortunately, I think I have left myself not enough room. And I'm confident that there's not enough room. So just a minute. I'm going to just switch over to my other app here. And we're going to add this stuff up. Okay, so here we go. Paste this in here. All right, so what we're going to be doing is we're going to take that distance and we're going to add up a bunch of distances. But before we do that, it would be helpful if I were to simplify this. Hopefully you can see what's going to happen with the simplification. This is going to equal the square root of delta x squared plus, there's not much we can do with this, x plus delta x minus f of x squared. Now, one thing that I know that I'm going to need, if I'm going to use the methods that we've been learning about in order to turn this into an integral, is I know that I'm going to need to have the sum of something times delta x. So you know this is the way that we did it when we were doing the work problems, when we were doing the washers and the discs and all of those volumes. We always came up with the sum of something times a delta x. It has a delta x, but it's not something times delta x. So I'm just going to do a little bit of algebra here, and then we will add this thing up. So remember, this is just one single distance, one single step along this arc length. So here's how this is going to look. Essentially, I'm going to factor out delta x squared, 1 plus, give me a sec here, f of x plus delta x minus f of x all over delta x. There we go. Oh, that should be squared. Okay, so let me explain what I just did, just so you don't get too scared. I've got well, maybe what you could do is think in terms of what this would look like if you were to just multiply this through. So if I multiply delta x squared times 1, I get the delta x squared up here. And if I multiply this delta x squared times this nasty thing, the delta x will cancel with the 1 in the denominator, and you indeed get this. So even if you don't believe me that I can factor out a delta x squared, well, I just did. So there you go. So then the next move that you're going to make is we're going to take that delta x squared and move it outside the radical. Technically, the square root of delta x squared is the absolute value of delta x, but we're going to assume delta x is positive, so we don't have to worry about that. So then we get this expression, 1 plus f of x plus delta x minus f of x all over. We're coming back to this, don't worry. Some of you can see ahead, can't you? And you know where this is heading. So now I finally have the sum, well, I have something times delta x. The something is that nasty radical. The delta x is just sitting there. So I'm going to take this thing, and I'm going to turn it into a summation. We're almost done, believe it or not. So let me just copy this. And so paste it down here, new line. There we go. So it's the same thing, but I'm going to do the summation of this thing over all of the little delta x's or all the little intervals, and then you're going to set this up with a limit as delta x approaches 0. Now there's one issue that we're going to have to talk about before we actually apply the fundamental theorem of calculus and get this into a nice integral, and that is what's going on with this thing right here. So let me just jot this down over on the side and see if anyone remembers what this is. So, or maybe I'll just put it below here. So what is the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x? And I'll give you a hint. You learned about this in Calc 1, and you tried your best to forget it because it was so painful. So what is that limit? Do you know? You remember, Red?
This is like the limit definition of the.
You got it. Come on, bring it.
So I forgot.
The limit definition of the. Someone help him.
Yeah.
It is. Wait, what is it? Wait, what is it? Oh, come on. It was already on the tip of your tongue. Who's got it? Someone else has it. You got it? It is the limit definition of the derivative. It's so beautiful, isn't it? So you do the limit as delta x approaches 0 of this thing, you actually get the derivative. Amazing. And so when I do this limit, what's going to happen to this is this will turn into an integral from a to b, whatever the thing is. And then this thing is still 1 plus, and this becomes f prime of x squared dx. Amazing. So there's the, isn't that incredible that all of this mess up here, it all got turned into this. So once again, I have snuck a proof into your course here. Thank you for enduring. I know that you engineers probably just want to see the formula. So let me get the formula for you. Give me a sec. Here it is right there. So the arc length is just the integral from a to b. So you're going over the entire length of whatever it is that you're trying to find the arc length for. 1 plus the derivative squared. Put that under a radical and you're all good. As you can imagine, this is usually not going to be very nice. And so we're going to have to be careful about which functions we put into this. Otherwise, we're just going to have to pull out our calculators and use the numerical integration on that. So all of the ones that I've chosen, and I think the ones on your homework, all come out reasonably nicely with a little bit of algebra. So I'll try to help you out with the algebra. But if you do get stuck, I suppose that's one thing. Write down the integral, show me you know what you're doing, and then you can use your calculator. I'll let you know on the test and on the quiz next time what you need to show me and what you can get by with the calculator. Okay, let's take a look at an example of this. I want to find that this is a nice, easy problem. One of the reasons why this is easy is because you could do this without calculus. So here, this is a straight line, and so there's almost nothing to do. You could do this, like I said, without calculus. But we're going to do this with calculus just to show you how this works. So to set this up, we have the integral from -1 to 3 of the square root of 1 plus the derivative squared. So I need someone to do my derivative, and Andrew wants to do it, don't you? Andrew, what's the derivative of that function up there? This one right here. Yeah, just 2. Sorry, I know. Haven't had your coffee, have you? So just 2. So this is just going to be 2. Take the derivative. Let me emphasize that that's what's going on. Pull over here. Y prime is equal to 2. And that's what's going into my formula for the arc length. And then we do dx. Almost too easy. You could do this in your head. But let's go ahead and finish this up. So this will be the integral from -1 to 3 of the square root of 5. And we'll find someone to do this antiderivative. I guess all of you need to wake up a little bit, perhaps. So Thomas, what do you think? What's the antiderivative of radical 5?
Radical 5x.
Oh, okay, radical 5x. Yeah, be careful. Some people will say, oh, it's going to be 5 to the 3 halves divided by 3 halves. No. 5 is just a number. Radical 5 is just a number as well. And so you have a constant, and this will be radical 5 times x, evaluated from -1 to 3. And so we're going to do radical 5 times 3 minus radical 5 times -1, which that becomes +1. So final answer is 4 radical 5. So far, so good. Anyone losing your minds yet? All right, excellent. Let's try another one. So here's one for you to start. So get this one started. This one is a little bit crazy, at least it looks a little crazy, but I'll show you how to work this one out. It'll be nice. So take a minute, see if you can work this one out. Yeah, it's just the length of this curve. Yeah, work with a friend. I know you have friends in here. Wow, you're really not talkative this morning. All right, well, yeah, it is cold outside. It's like starting a car. You just have to take your time. But Eli, what's the first thing you did to do this? You don't have to do the whole thing. Just get me started.
Just copy that down.
Excellent. Thank you, Eli. I appreciate that. You copied it down. All right. Well done. Okay. Michael G. Michael, what did you do after you copied it down?
I took the derivative.
Excellent. I like to tell students, in calculus, when in doubt, do a derivative, right? What is the derivative, Michael?
Is it 9x to the 1/2?
9x to the 1/2. Beautiful. So if you need me to, I can talk you through this, but it's a pretty straightforward derivative. Multiply by 3 halves, and then subtract 1 from that 3 halves. Well done. All right, Braden. To put my glasses on. All right, Braden, what's next? What's the next thing you did? All right, talk me through it.
The definite integral of 0 to 1, square root of 1 plus y prime, which is minus 1/2 dx.
Like that?
Yeah.
Is there? Oh, yeah, yeah, squared, good, good. Yeah, I think you probably have the square, it's just, I wrote down exactly what you said, so, very nice. So let's go ahead and work through this. Can't be that hard, could it? So let's see. This will equal, let's see if we can simplify this. Why don't I do this next step for you? 1 plus 81x. Does that look right? When you square 9 times the square root of x, you get 81x. All right, so now we just need the antiderivative of this, and we can use integration by substitution if you need to, or if you can just do it, that's even better. So this one is pretty easy. Anytime there's a linear function like this that I'm going to substitute for, I usually skip the whole substitution. But I can do substitution if you want me to. Maggie, what would you like me to do? Should we actually write down the substitution, or do you just want to do the answer?
Write it down.
Okay, let's do it. So what would u be for this?
1 plus 81x.
All right, and then du?
1 dx.
81, did you say, dx? Very good. Okay, so to do this, I'm going to have to do a little rearranging. So let's go ahead and do this. This is going to be the integral of 1 over 81 radical 1 plus 81x times 81 dx. So you see I've done my algebra so that I have the du is right there. So, and I encourage you this way, if you do it this way, you will not get it wrong when you do substitution. Some of you are still struggling with substitution. And so, oh, and I've left off the limits because I don't like to keep my limits around when I'm doing substitution. I mean, I'm happy to put them in, but I'd have to change them to values of u, and that usually causes issues with students. Okay, very nice. So this is perfect. Good job. Next, let's find our next volunteer. Caleb. Caleb, I know you might have just done the integral like this, but let's humor those who want to do it this way. What is the antiderivative of the square root of u? Do you know?
2/3 u to the 2/2000.
Very nice. Okay, that's beautiful. So well done. So now we're just going to put our substitution back in. So let's see, I'll make some room over here. Give me a sec, and then we'll see how we did. So, and this is where I'll bring back the limits, just because I know that the limits are sometimes difficult for you guys to, here, let's see, this is going to be 1 plus 81x. Yeah, I'll explain what I mean by, just a minute, that's a 0. Okay, just so you know what I mean by changing the limits. It is possible, if you wanted to, you could change the limits to values of u down here. That's the way I prefer, but I've been told by various students in the past that they prefer not. So, but if you want to, the key is that if you change to u, then you should never go back to x. You should plug in your values of u. Specifically, when x equals 0, u equals 1. When x equals 1, u equals 82. So I would change, here, I'll just do that just briefly. I know we've talked about this before, but just in case. So you could do that, but I've realized I've actually pulled students in the past, and this seems to be preferable. Okay, let's go ahead and plug these things in. So 2 over 243 times, wait a minute, I left something out, didn't I? Sorry, in all my excitement about my limits, I forgot my power. There it is. Okay, so 2 over 243 times 82 to the 3/2 minus 2 over 243. That looks pretty good, doesn't it? But I suppose you might say, let's do this. 2 times 82, radical 82. I mean, I'm happy with, you box this up here and you're going to get your smiley face. But you could simplify it if you want. There you go. Any issues, questions, concerns? All right, let's go and take a look at these. Get a little bit harder as we go along. Whoops, not that one. Whoops, we did this. Okay, let's, yeah, I really want to get onto this one. I guess we could do this. This is fine. So you'll notice that this one, I want to find the formula, or use the arc length formula to find the arc length of this curve where x goes, whoa, x goes between 0 and 2. So the issue here is that you have y squared equals this stuff. So technically what you're looking at is you're looking at a curve. Let's see, x plus 4. Just a minute. I haven't left myself enough room over here. Here's what I'm going to have to do. I'll just copy this over to Notability. So, come on, go back. Oh. There. Okay, so the issue here is that this particular curve it's not a function. So here I'll draw this curve as best I can. So this looks something like this. 0, yeah, it's gonna be really big. Something like that. This point right here is going to be 4 to the 4th, which is 256. Is that right? So that's where it crosses the y-axis. Same thing down here. If you plug x equals 0 into this, that's what you get. So you've got this weird curve here that goes back. So when we say x is between 0 and 2, or which of these are we talking about? You've got this branch of this function and this branch that goes in 2 different directions. So I'm just going to focus on this one up here, as we're going to see if you let y, or if you take this thing and do the square root of both sides, you get this. And so you get both of those branches. Like I said, this isn't a function, positive and negative. So you're going to want to just focus on one of them. I suppose we could add the 2 together to say, oh, it's going to be that plus that, but this will be fine. So let's go with this function, just the positive branch. And I guess the square root of 4 is 2. And so this is x plus 4 to the 3rd. And let me simplify it one more time and then turn you loose to go ahead and do this one. So go ahead. Oh, and then the limits are that. Go ahead and see how far you can get with this in the next 2 minutes, because I need to show you a couple more of these before, let you try a few more of these before we go. So see how far you can get, and then we'll see where you are. And if you need help, you can always call me over or ask your friend. Since some of you are done, I don't want to bore them, but let's go ahead and get this started. Landon, you know the first step. Do a derivative, right? Landon, what is the derivative to this function? Very nice. 3x plus 4 to the 1/2 power. Beautiful. So let's find our next volunteer. Ethan, what's the integral going to look like for this arc length?
I messed up
All right, well, talk me through it, and I'll do the algebra for you.
The formula for dark one?
Yeah.
Oh, that's the integral from 0 to 2, square root 1 plus 1 derivative squared.
Okay, so we're going to take this derivative, x plus 4, and we're going to square it. Oh, sorry about that. There, does that look good? I know, it doesn't look good at all. My handwriting was poor, but that's what you were saying, right? Okay, let me clean this up just a bit, and then we'll see where it ended up. So we've got 1 plus 9 times x plus 4. Because the square root of x plus 4, when you square that, you just get x plus 4. And then this, I'll just clean up a little bit more. So this is going to be 37 plus 9x. How's that look? All right, so here we have that choice that we can make. And we did the substitution on the previous problem. Let me just remind you how you would do this. Whenever you have a linear function like this, you know what the substitution is going to be. I'll talk you through it. The u is going to be 37 plus 9x. The derivative du will be 9dx. And so you're going to have a 1/9 somewhere, just like up here, wherever it was. We ended up with a 1/81st, I think it was. So we're going to have a 1/9 in here somewhere. And so I'll just put it right here. And then you know that u to the 1/2, when you do the integral, will be u to the 3/2 times 2/3. And that's what we're going to evaluate from 0 to 3. So then from the rest of this is pretty straightforward. Once again, this isn't going to be all that satisfying because when you plug 3 into this, what is this? 81 plus 37. What's that? Oh, it is. Thank you. Save me from myself. Let's try again. Okay, the rest of it is good though. So I did have 2 coffees this morning, but still, apparently my brain isn't fully functional. Okay, so a 2 up there, thank you. Anyway, so we have 2/27 times, I'll do this more carefully, 37 plus 18 is 55. All right, not getting a lot of love from you. 55, so we got 55 to the 3/2 minus 2/27 times, let's see, 37 plus 0, which is just 37 to the 3/2. And I'm just going to leave it like that. Although the back of the book, if you were looking in the back of the book, you probably are going to see something like this. 55 minus 74, radical 37 over 27. So don't be scared if the back of the book answer doesn't quite look like yours. You can always punch both of those into a calculator and figure out whether or not you're right. If it's the same decimal, then you're probably right. Okay, a couple more, and then we'll call it a day, and you'll be able to go play in the sun or the snow. Here we are, arc length of this function. I love this one. Actually, this one's kind of one of several that are like this. But this one I kind of like because of how this shakes out. So let's work through this one together because the algebra is a little bit challenging and but it's interesting the way that this works out. So first things first, we need the derivative. Go ahead and jot your derivative down for this function. And that's 1/8. I know it got cut off down there. I'll just make it into an 8. There. So find your derivative. Americo, once you get it, let me know what you get for this derivative. I'll just write it like this if that's okay. Same thing. Very nice. Okay, so let's clean this up just a bit. So there's the derivative, and that's what we're going to stick into the arc length formula. Take a minute, write down that arc length formula. The more times you write these things down, the more likely it is that you'll remember it, just like with the integration by parts formula that I said, write it down every time. So this will be a similar situation. Hopefully you'll remember later. So length. So take a minute, jot it down. I'll pick someone to recite what you have there. Hunter, what did you write down for your arc length formula?
The integral from 1 to 3,
All right.
square root of 1 plus 2x minus 1 over 8x squared.
Beautiful. dx, of course, right?
Yeah.
Very nice. This one is kind of cute. Let me just copy this over to Notability so that I can have more room. So the arc length is the integral. Hunter, help me out again. What are the limits?
1 and 3.
Oh, 1 and 3, okay. 1 and 3, 1 plus 2x plus 1, or was it minus?
This is minus.
That's right. Give me a sec here. Minus 1 over 8x, quantity squared, there. Yeah, let me run through the algebra with you. This, I don't know, I just love it when something like this happens where you have something that looks like it's impossible, and with a little bit of algebra, it turns out it's actually quite simple. So let me go through this. So this thing, okay, 1 to 3. Let me do squaring a binomial first. So 4x squared minus twice the product of the two terms, 2x times 1 over 8x. And then the second thing squared, that's going to be 1 over 64x squared. So if you didn't remember squaring a binomial formula, you could always just do FOIL with that, which I know some of you love. So however you cut it, you're going to get this expression. The cool thing that happens with this is that inner term, or the inner and outer terms, I guess. So this is 1 plus 4x squared minus 1/2, because the x's cancel and 2 times 2 cancels with the 8, and you're just left with 1/2. And then 1 over 64x squared. Almost there. Then we can do this, 4x squared plus 1/2 plus 1 over 64x squared. Okay, at this point, some of you might recognize that that looks suspiciously like the thing that I have written here, there, which is this thing squared. And if you recognize that, then you can probably disentangle it and figure out how to factor it. But I'm going to assume, not assume, I'll just say that I'm going to go through this pretending that I don't see that. And so my next move might be to write this as a single fraction, something like this. So this is over 64x squared. This will be a 1. This will be 32x squared. By the way, I'm just right, common denominator is 64x squared. And then this first thing I have to multiply, that's going to be what, 256? The x to the 4th. How's that look? Now, you might notice, maybe not, that top trinomial is a perfect square. And the bottom thing, of course, is a perfect square. So I'm not sure if you would notice that or not, but you can factor that top, the numerator of that fraction. I know it's a little uncomfortable to think of it as, it's a fourth power there, but that's what that's going to look like. And then we can do the square root. And because we're dealing with only positive values of x, I don't have to worry about an absolute value. But anyway, here, I'll just write this right here. And then you'll be able to do this yourselves. So this is going to be 16x squared plus 1 over 8x. Isn't that incredible that it actually factors and you're able to get rid of the radical? Okay, so then this thing becomes this. So 2x plus 1 over x, 8x. And just to make it, well, no, I'll leave it like that. No. I'll do one more thing. And then I'll zoom out so you can see all of this glorious algebra. There it is. Okay. I don't know if that's enough for you to see and enjoy. You can always watch the video later, pause it, see all the incredible stuff. But anyway, down here at the bottom now, everyone here can do that antiderivative. So I'll just pick someone. Karen, what's the antiderivative of that thing that we've got there now? So what's the antiderivative of 2x? It's x to the first. You're going to add 1 to that power. So what's 1 plus 1? 2. Yeah, very good. So that's going to be x squared, and then divide by, what do you divide by? 2. Very good. Okay, good. So then we need the other piece. So Maggie, what about that other thing? What's the antiderivative of 1/8 times 1 over x?
1 over 8 natural log x.
Very nice of the absolute value of x, but as I mentioned, we're dealing with positive values here, so I guess it really doesn't matter if you leave the absolute value off. Very nice. Onward. Let's plug these things in. I get 9 plus 1/8 natural log of 3 minus 1 plus 1/8 natural log of 1. I suppose you could just box that up, but you should be a little embarrassed if you just box that up and leave it like that, because this natural log of 1 is 0, you should know that, and this becomes 8 plus 1/8 natural log of 3. Wow, that was so much work, wasn't it? Look at all that. But I guess, to me, I love it when things come out so nicely like this. And there it is. Let's see, what time is, oh, you're all packing up? Yeah, it's about time to go. Well, thanks for sticking around for 1 minute extra. I'm going to stop the recording if you want to come chat. Otherwise, there is homework for tomorrow. And don't forget, look at the practice test before tomorrow, if only to say, these are the topics that we need to cover in our practice time.